Now we want to talk about the idea of solubility and focus in on ionic compounds. So we've talked a lot about the properties of solutions and when compounds dissolve, what it looks like when they form solutions. But just because we can write out the equation of what it would look like for a compound to dissolve in water, it doesn't mean that compound actually will. So the idea of solubility is that for a given solute and solvent pair, soluble means they will form a solution, and insoluble means they won't. Normally, this designation is applied to the solute. So we pick a solvent. So for example, water. And so we would say like sugar is soluble in water. If you put it into water, it's going to dissolve. But like oil is not soluble in water because it doesn't mix with water. It doesn't dissolve in water. And so this is going to depend. You need to know both the solvent and the solute. There is no solvent that everything is soluble in, and there's no solute that is soluble in everything. You have to know both substances, both compounds that you're looking at in order to figure out whether or not they're soluble. And so when we define solubility, we normally think about this as kind of a binary, something either is or isn't soluble. But there's a lot more nuance to it than that. And so a saturated solution is a solution that has the maximum possible amount of a given solute. So for example, we said salt. We've all dissolved salt in water or gone to the beach. There's a bunch of salt dissolved in that water. And so if you take, say, 100 milliliters of water and you put 30 grams of sodium chloride, some table salt in there, it just fully dissolves. You end up with a solution that looks like water, right? It just still looks like water. It maintains all of those properties. If you keep adding salt, though, say 40 grams, you hit a limit. Not all of the salt dissolves. If you have 100 milliliters of water, you can only dissolve 36 grams of sodium chloride. So that's a ton of sodium chloride that you can get to dissolve in there, but the rest of it will not dissolve. There's 4 grams that stays solid because it can't fully dissolve, okay? And so even though there is a limit, you can't just dissolve hundreds of pounds of sodium chloride into water. You can still dissolve a lot. And so we would still say sodium chloride is soluble. There is just a limit to that solubility. So when we say something is soluble, generally what we mean is that you can get a good amount dissolved in that solution. Specifically, if we look at this limit, every compound has a limit. So for example, sodium chloride, we say that's something that is soluble in water. So 36 grams is the limit for 100 milliliters of water. So what that really means is 36 grams. If you put 36 grams of salt into 100 milliliters of water, you're really going to affect the properties. It is very different than pure water. Something that is considered insoluble, like for example, silver chloride, the limit, that maximum, that saturation is reached at 5.2 times 10 to the negative 4th grams. That's 0.5 milligrams. That is barely anything that dissolves, especially in 100 milliliters of water. You really haven't affected much what's going on. So when we talk about something as being insoluble, what that really means is you can't get enough dissolved in that solvent of choice to really cause any effect. If I'm trying to, say, run a reaction where silver chloride is one of my reactants, dissolving into water is not going to help me, right? Because barely any silver chloride is dissolved. It's really not doing anything. We will eventually circle back to this idea, how much silver chloride is out in there and what it can do. But for now, we're just going to say that's not really enough to perform any sort of reactions or affect the properties of a solution in like a really meaningful way. So now that we know what solubility means, this idea that we can get enough dissolved into solutions, we want to start talking about the idea of predicting whether or not two different substances will form a solution. And the general guideline for solubility is going to be the idea like dissolves like. And when we use this, what we're applying it to is polarity. So it's back. So what that means is polar solvents tend to dissolve polar solutes, and non-polar solvents tend to dissolve non-polar solutes. Polar solvents do not tend to dissolve non-polar solutes. You do not usually find any mixing. It's not going to be perfect. Just because two things are polar doesn't mean they do form a solution, but generally there's nothing that really crosses over. And so this is a guideline, a rule. This is not hard and fast. This isn't a law or anything like that. But this is a general guideline that we can use to figure out whether or not, or make predictions about whether or not something is soluble. And this does apply to both ionic and covalent compounds. So when we apply it to ionic compounds, what we can say is, first off, ionic compounds are only soluble in polar solvents. If you remember, the whole point of polarity is that, for example, in a water molecule, you have, say, a positive side to the molecule and a negative side to the molecule. And so you have one side of each. In an ion, you just have a positive object or a negative object. And so you can think of ions as being polar to the extreme. It's not that they have a positive side and a negative side, they just are positive or are negative. And so ionic compounds only dissolve in polar solvents. They never dissolve in nonpolar solvents. Now, not all ionic compounds are soluble in polar solvents. And our most common polar solvent is water, really the only one you're hopefully ever going to interact with, and really the only one that we use. And so why, what is going on here? Why do polar things only dissolve in polar solvents? Well, the reason is, we talked about the idea that when an ionic compound dissolves, all of these ionic bonds are going to break. Okay, so you're breaking chemical bonds. And what you replace them with is called a hydration interaction. And so because your water molecule is polar, all of those negative ends, say the negative end around each of the oxygens, can interact with the positive cation. So that's when the positive cation separates out from the negative anion, it can interact with a bunch of water molecules. And at the same time, the positive ends of other water molecules can interact with, say, the anion. Okay, so you can interact with the opposite charges. And so yes, you break an ionic, a chemical bond between your pair of ions, but you form all of these hydration interactions where the positive or negative anions are interacting with the polar water molecules. And so that interaction with polarity is what drives the solubility. There is an interaction, an intermolecular interaction, that makes up for breaking those ionic bonds. When it comes to predicting whether or not an ionic compound is soluble, one of the things we know is if your solvent isn't water, it's not soluble. Okay, so that's easy. If your solvent is water, we have some rules, and those rules are based around the ions that are present in the ionic compound, because we know ionic compounds separate out into the different ions, so the two different ions will each form hydration interactions. Some ions form really good hydration interactions. Those tend to be soluble. Other ions don't form strong hydration interactions. They tend to not be soluble in water. So we have these rules, and you can see the rules are ordered in number. 1 is the most important rule, 7 is the least important rule. So we want to go through these rules in order and take a look at what they are. These rules are posted in the additional resources folder on the Blackboard page. I encourage you to take a look at them, to use them. You'll note there are lists of ions. You can use them in conjunction with the polyatomic ions list, that sort of information to help you parse these things out. One of the things, you may have learned a different way to learn ionic solubility. Certain ions have a tendency or other things like that, different tables. If you have a preference to use those, that's fine. You don't have to use the rules that I use. I like these rules because I think they kind of give you a kind of a logical framework or an algorithm, which I like. But as long as you're predicting solubility correctly, I don't care how you do it. The one thing about these rules is because they're in order, these top rules are the most important. So you kind of start to get a tendency, group 1A compounds, the alkali metals. So sodium, potassium, lithium, those are the things we tend to see pop up in lab a lot as cations because they're always soluble. Nitrate, very, very common anion that we use in the lab because it's always soluble. As we go down, again, these preferences are almost always true. These aren't as strong of preferences as the top ones. And then finally at the bottom, these are the least strong preferences. you know, compounds with 2- or 3- anions tend to be insoluble. But if rule 1 through 5 kicks in, that's more important. And so that would take precedence. That would determine whether or not you had actual solubility. Let's look at some examples. Are the following salts soluble in water? I have sodium phosphate, ammonium sulfide, calcium chloride, silver chloride, and silver nitrate. All right, so the first thing whenever we're deciding solubility is always to figure out what are the ions. So when we see sodium, that's a metal. We know this is an ionic compound. That's an element that's just going to cut off. And so our ions are going to be sodium and phosphate. So PO4, if we can always use the periodic table to know that sodium is +1. For phosphate, when we see PO4 as this whole ion, one thing we can do is we can look it up in the periodic table, or we can look it up in a table of polyatomics, or we just know that it's 3-. It's going to be worthwhile because some of the rules are based on the size of the charge. It actually doesn't matter here because when you see sodium, when sodium is in the front right here, sodium is in group 1A on the periodic table. It's an alkali metal, so it's soluble. Rule 1 says that it's soluble. You'll note there's a rule that says 3- tends to not be soluble, but we don't care because the Na+ is a higher priority. That's rule 1. Sodium compounds are always soluble. It doesn't matter what sodium is paired with. You're done. It is always soluble. All right, NH4,2S, that's ammonium sulfide. So we want to be careful with this here, especially ammonium. One of the things, those parentheses tell us that that is a polyatomic ion. We definitely want to be on the lookout for ammonium here, NH4, because that is a polyatomic ion that is special, that it is also part of rule 1, where it is always soluble. Again, it doesn't matter what it's paired with. In this case, it's sulfide. Sulfide is another one that would trip on the 2- rule, pretending to be not soluble, but it's paired with ammonium. Ammonium is rule 1. That is the most important rule. This thing is a soluble compound. All right, calcium chloride then. And break that off. If we have 2 atoms right there, calcium is a metal, so we know it's ionic. We want to look at our 2 ions then. It's calcium and chloride. Calcium doesn't really have any rules. There's no rules associated with it, but we can see that chloride, we do have to go all the way down to rule 4. So rule 1 is about the group 1As and ammonium, so that's not it. Rule 2 is about some polyatomic anions. That's not it. Rule 3 is about silver, lead, and mercury. Those aren't here, so we get to rule 4. That's chloride. And so chlorides tend to be soluble. So calcium chloride is soluble, and we would say it's by rule 4. So chloride is kind of encouraging this compound to dissolve in water. If we then look at silver chloride, so similar idea, but in the case of silver chloride, chloride, if we could see, is rule 4. Silver is rule 3. So because it's at rule 3, that is a more important rule, and silver chloride is going to be insoluble. You think chloride has a tendency to want to dissolve. Chloride ions form relatively strong hydration interactions with water. Silver does not. Silver does not form strong hydration interactions, so it does not dissolve. It stays in the solid, and so it stays right in there in the solid. It does not tend to dissolve out and float around in solution. So there's relative preferences here. If we then make it silver nitrate, now we're dealing with silver and nitrate. And nitrate, NO3-, my polyatomic, rule 2 says that is always soluble. So because rule 2 is above rule 3, nitrate, this compound is soluble. So chloride, you can think of in this case as like the weakest preference. Chloride tends to want to dissolve, but silver trumps it. So if you pair silver with the chloride, it won't dissolve, but nitrate really wants to dissolve. So nitrate compounds are always soluble. It doesn't matter what nitrate's paired with, it's going to be a soluble compound. Silver nitrate is soluble in water. Participation 9.4, question 2. Determine whether each of the following ionic compounds is soluble in water. A, LiF, B, Al2CO33, C, BaSO4, D, NH4NO3. Is the second question on participation 9-4, due Friday, September 4th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, determine whether each of the following ionic compounds is soluble in water. A, lithium fluoride, B, aluminum carbonate, C, barium sulfate, and D, ammonium nitrate. Hopefully these compounds look a little familiar. You can use some analysis or some stuff you've already figured out about these compounds. All right, another participation question for the 9-4 assignment in this video. See more videos to go. I'm finding more questions for participation 9-4. See you in the next video. Bye.